We are in the NTB coordinate system, and one of the cases that we need to consider are those that occur on a flat surface, and we will call those flat track problems. So vehicles going around a corner, or something sitting on a rotating table, or conveyors are examples of this type of problem. And in all cases, what keeps the box on the conveyor, or the girl on the rotating table, or the car on the road, what keeps these things is friction. And at the point where the friction available might be less than the friction required, then that's when you leave the road or the table or the conveyor. So these are three-dimensional problems. The equations of motion and the NTB equation of motions apply, and we're only going to consider constant radius problems for now. So let's look how we would describe this type of problem with a three-body diagram. So we're going to look at this from the top view first. And so let's say that there's something on the table. There's going to be a velocity that is going to be tangent to the path. There may be a rotating situation here where the table or the car may have some theta dot. The tangent axis is going to be in the direction of motion. So this will be the tangent axis. The normal axis points in toward the center of rotation. So the normal positive normal axis goes this way. There will be forces, and the forces that will cause this motion, there will be a force in the tangent direction, and there will be a force in the normal direction. And those are both friction forces. The only forces that we have in this problem are friction forces. The only forces we need to really consider are friction forces. Force in the normal direction. Let's look at this from the side view. And from the side, we have this box sitting on the table. There will be an mg coming down and a normal force going up. The normal axis is again pointing straight in. The b-axis is going up like this. The tangent axis actually comes in and out of the page. Tangent comes in and out of the page. Okay. This is mg, all right. So where's the friction force? Well, the friction force, you can't really see all of the components here, but the friction forces will be in this direction, or you can sort of see it like that. And the friction force will be the sum of the vector sum of the force normal, the force of friction normal, and the force of friction tangential. These are both friction forces up here. All right, now don't get confused. I wish there were more conventions or more letters perhaps, but this normal force here is not the same as this force in the normal direction. They are different, and we just need to kind of keep those straight. We'll probably use the same terminology, unfortunately, for both of them. Okay. So let's look at this box that's resting on the surface of this disk. The disk then begins to rotate, and as you'd expect, as it starts to go, that pretty soon the box will slide off. There is a coefficient of friction that's given as 0.8, and we want to find out how much time it takes for this box to slide off. So let's draw the free body diagram, the top view first. And so we know that there's a velocity, and there is a theta double dot, which is the angular acceleration. The tangent axis goes in this direction. That's the direction of the velocity. The normal axis would go in this direction. There would be two forces that we need to consider. So there'll be a force in the tangent direction and a force in the normal direction. Both of those are friction forces. Let's look at the side view. So the side view looks like this. Again, there's an mg, a normal force, and a force of friction that we can't really see the two components of, but it kind of goes in that direction. Again, the normal axis goes this way. The b-axis is going up like that. All right, let's draw let's write the equations of motion for these two forces. Okay, so if we if we look at the forces in the tangent axis, the force in the tangent axis is equal to mass times acceleration in the tangent axis. What is that force? Well, the acceleration in the tangent axis, theta, the angular acceleration is theta double dot, and so we know that the acceleration in the tangent axis, A tangent, is equal to r theta double dot, and this r is given as 2 meters, and theta double dot is 0.75, so this is equal to 1.5 meters per second squared. Okay, how about the force in the normal direction? The force in the normal direction is equal to ma normal, and we know that is equal to mv squared over rho. Now the velocity here is an unknown. The rho, or the radius, is 2, so we can say that that is mv squared over 2 meters. All right. Now the thing to note here is that the force of friction is the vector sum of both of these things. So if I draw a little vector box here, I can say that the force total is going to be my total force of friction, F total. And I can say that the force total is equal to the force of friction. And if you look at the side view, the force of friction, as it begins to slip, is going to be equal to mu normal, which is equal to mu mg. The force total is also the vector sum of those two guys. So I'm just going to put those together. F total is equal to the square root of F tangent squared plus F normal squared. And I'm just going to put in the values here, or put them together. So I'll say mu mg, is my total force, is equal to the square root of, well, it's going to be the m times a tangent squared, that's force tangent, plus mv squared over rho, the quantity squared, inside the radical. Now I am going to take this, now I'm going to square both sides, so I'm just going to do that to that, and call that squared like that. All right, now I have mass that's actually occurring in every term, and so in this case, I'm lucky enough that I can cancel that mass. So I'm just going to say mu g squared. Well, let's just go ahead and write the numbers in. We have 0.8 times 9.81 quantity squared is equal to the acceleration in the tangent direction is 1.5 squared plus v, in this case, is v to the 4th over rho is 2 squared. And I can solve that for the velocity, and this is the velocity at which it falls off. So v max is equal to 3.925 meters per second. Now that's a preliminary answer because we're looking for the time, but we know that as things go around a corner, the velocity in the tangent direction is equal to the acceleration in the tangent direction times time, times the time, and I can solve that for the time is equal to 3.925 over the, that's the velocity, over the 1.5 is the tangent acceleration, and that's equal to 2.617 seconds. And that's how long it takes for the box to begin to slide, and then these things don't apply anymore. The next scenario to consider is where an object rotates around a circle, but the surface is at an angle to the horizontal. This airplane or this carnival ride are good examples. In these cases, there is lift or tension in the rope, keeping them on their path. The other ones to consider are like this collar on this angled rotating shaft. The shaft is rotating and the collar could slide up or slide down, or this car problem where race cars, obviously, where they could slide probably up the track or off the track if they go too fast. In these two cases, friction is what keeps them on the path, and we're going to call all of these types of problems banked track problems. So banked track is what we're going to call these. All right, so these are three-dimensional problems. We're only going to consider constant radius and constant speed problems, and when constant speed happens, that means that the acceleration in the tangent direction is equal to 0. So let's look at the free body diagram. From the top, we have an object that has a velocity, and the tangent direction will be in the direction of the velocity. The normal direction points in toward the center of rotation, or the center of the circle, and that's really all we'll look at on the top view, but the side view is where the interest is. And here we'll have an object that is resting on the banked track, it'll have a gravity going down, an mg. The b-axis goes up and out of the, or up like that. The normal axis points in toward the center of rotation, or at the center of the circle, and there will be a normal force. And the normal force is perpendicular to the surface. There may also be a friction force, either going up the hill or down the hill, but that'll be parallel to the surface. The distance r is going to be the constant radius, will be the distance from the object to the actual point or actual center of the circle, or to the center, to the distance. It'll be the distance to the point of rotation, or the distance to the center of the circle. So the problem I'd like us to consider here is this guy, this man is leaning on this surface, and the surface is somehow tied to the center here, and it's rotating about that point, and so that he's rotating about in a circle. And you can see that if he wasn't rotating, he might have a tendency to slide down, but if he rotates too fast, possibility he could slide up. So anyway, what we're looking for is at a particular speed, we want to find the friction required to keep him from sliding down. So let's look at the top view. Top view is that looks like this. He's got a speed going this way. This will be the tangent axis. This is the normal axis. And then from the side view, we're going to say that this is the whole thing, and he's got an mg going down. There will be a normal force going this way. Well, let's draw the b-axis. The b-axis goes up like this. The n-axis goes toward the center of the rotation. The normal force that we will consider is perpendicular to the surface. So the problem I'd like us to consider here is that this guy is leaning on this mat or this cushion, and he's rotating about the center. There's some mechanism here, like a carnival ride or something like that, that allows him to be tied there, and it's going to be rotating like that. So you can see that if there was no rotation, he might have a tendency to slide down. If he rotates too fast, he might slide up. But in this case, we're going to give it a speed and an angle, and we want to find out how much friction is required to keep him from sliding down. All right. So let's look at the free body diagram. That the top view says that he's going to be going in this direction, tangent to the path, and the normal direction is going to be in like this. If we look at the side view, we've got this guy, and he looks like it's going to go. He's got a weight going straight down, and the b-axis will be going up like that. The normal axis comes from his body, goes to the center of the point of rotation. There will be a normal force, and we'll call that normal force, which is perpendicular to the cushion going in this direction. And what we want to do is find the components of the normal force there's also going to be friction. Friction force is going like this. And what we want to do is find the components of these forces in the b and the normal direction. So I'm just going to draw those components. I'm going to say that there's going to be a force of friction, and let's put our angle in here. This got an angle of theta, which means that is angle theta, which means that this is angle theta, like that. So if that's the case, the force of friction going up in the b direction is going to be, this is going to be force of friction sine theta, and there will be a component going this way, force of friction cosine theta. The normal force will have a force of friction, or we'll have a normal force going up this way, or a component of the normal force, and that'll be normal cosine theta, and this will have normal sine theta. All right. If you can look at the trig, you can see all those pieces. And what we want to do is sum the forces in the normal and in the b direction in order to discover our solution. So just another thing to note, this normal force here is perpendicular to the surface, but it is not to be confused with the components in the normal direction. This is the normal direction, but these are the components of these other forces in the normal direction. And again, that's not the same as the big N normal force. And again, I wish we had a slightly different convention, but we don't, and so we'll have to deal with this. All right, so what do? Let's sum the forces in the normal direction and see what we get. So I'll just say sum of the forces normal is equal to mass times acceleration normal. What I got there is in the normal direction, I have, again, positive normal points in, so I'll have n sine theta minus force of friction cosine theta. That's equal to mv squared over rho. So let's see what we got. At the point of slipping, and what we're going to say at slip, which is what we're looking for is at the limit, force of friction is equal to mu normal, which we should know. And so I'll say n sine 70 minus mu n cos 70 is equal to the mass. And the mass is how much? This guy has a weight of 150 pounds. So let me do this over there. Weight of 150 pounds, so the mass is going to be 150 over 32.2. The velocity was given as 15 squared, so 15 squared, and rho is 8 feet. All right, so we'll put all these things together and we'll see that the normal force is described like this. All right, now let's see what happens in the tangent, or in the b direction. So let's sum the forces in the b direction and see what we get. Sum of the forces b is equal to 0. Now the reason the sum of the forces in the b is equal to 0 is we are not allowed to move in the b direction and still stay on the path. So let's see what we got. Minus mg. That's this one going down, and b is positive going up, so I have minus mg plus n cos 70 plus force of friction sine 70, and that's equal to 0. So I can solve this for the normal, and minus 150 is the mg minus normal cos 70 plus force of friction here is mu normal, so it'll be mu normal sine 70 equals 0. All right, so now that I've solved this for the normal force in the b direction, I will circle around that. And now I have two equations, two unknowns. I have a normal force that's unknown, and I have a mu that's unknown, so I can equate those two. So now I've done the algebra, and I've put those things together. And if you solve this for mu, you can see that mu is equal to 0.551. And that is the coefficient of friction required then to keep him on the path or keep him from sliding down the hill.